All right, let's look at variance. Do you remember from the first lecture in chapter 4, we talked about how we need to include this -1 here in the formula for variance. And I said it was a correction. When we looked at the formula, the definitional formula for variance of the sample, all right, we said all you have to do is figure out the average squared distance that scores are to the mean. Okay, so the average squared distance that these scores are to the mean. And since it's a population, the mean is mu. Okay, and the squared tells us that we're squaring all the distances. You add up all these squared distances, divide by n, and that tells you the average squared distance that x is to mu. Now, what about if we are calculating variance of the sample? Well, if it's the sample, then we have to put x bar here. It's no longer mu, right? It's x bar. So s squared is the average squared distance that x is to x bar. You would think then that we should just have little n, the size of the sample, in our formula, but no, I snuck in a -1, and again, I said it's a correction. So now I want you to appreciate why we're putting in the -1. If we didn't have the -1 here, then the variance of the sample would be biased. Okay, without -1, without this would be biased. So as long as we include 1, okay, the -1, s squared is an unbiased estimate of sigma squared as long as n minus 1 is used in the formula. You've got to put in this correction, okay? In fact, if you didn't have the -1, s squared, the variance of the sample, would have a consistent tendency to underestimate the variance in the population. And if it has that consistent tendency to underestimate, that means it's biased, right? Go back to the definition of what it means to be biased. An estimate is biased if it has a consistent tendency to either underestimate or overestimate the parameter. Here we're seeing that s squared would have a consistent tendency to underestimate the variance in the population. That would make it biased. So that means that we can't say, or I should say, we can say, as long as we use that -1, we can say that the expected value of s squared equals sigma squared. It's unbiased. And again, somebody figured this out years and years and years ago. And it was figured out that as long as we use -1, we can write the expected value of s squared equals sigma squared. Okay? How did they figure that out? How did anybody figure out that all you have to do is put a -1 here? I don't know. I mean, I have such respect, huge respect for mathematicians, because I don't know how they figure this stuff out. I mean, was it an accidental mistake where somebody just said, ooh, let's just try -1. You know, they were drunk one night and said, I'm going to try the simplest correction possible. And let's just put -1 in there, and lo and behold, it worked out. I have no idea. Okay, now that we know that x bar is unbiased and s squared is unbiased, what about s? After all, s, which is the standard deviation of the sample, s is merely the square root of variance, right? Take your s squared, square root it, and that gives you s. So shouldn't s also be unbiased? Well, you would think so. It's not. S is always biased. Always. Even with the -1, it's still biased. Now, you might want to know, well, why? All right, I asked that same question. Why is it that s squared is unbiased, but s is biased? And I've never found an answer. In fact, if you were to pick up any other textbook in statistics, I can pretty much guarantee you that you're going to come across one of two answers. Either you're going to read that the explanation is beyond the scope of this book, which is fair. Maybe it's going to take 20 pages to explain, and it's not that important, right? So maybe that's it. But that's one explanation. The other explanation is somebody's going to say, well, the square root did something. Well, duh. The square root obviously did something. It took you from s squared to s, so yeah, it did something. But why did it take an unbiased statistic and then create a biased one? And again, there's a reason for it, but I just don't know what it is. So what about this? If s is biased, why do we use it? Because remember I said that s is standard deviation, is the most frequently used measure of variability. But if it's biased, why do we still keep using it? Why is it the most frequent? And the answer is, it's only a little teeny tiny bit biased. It's not biased by very much. And so the advantages of using S far outweigh the disadvantages. It's like, yeah, well, nobody's perfect. But it's pretty good. S is good. It's not flawless, but it's good enough. It's better than using s squared. Okay?